Assalamu alaikum. Today I want to talk about chapter 21, lipid metabolism. In part 1, I'm going to cover section 1, lipids are involved in the generation and storage of energy. Section 2, catabolism of lipids. Section 3, the energy yield from the oxidation of fatty acids. Section 4, catabolism of unsaturated fatty acids and odd carbon fatty acids. And in section 5, ketone. So let's start with section 21.1. Lipids are involved in the generation and storage of energy. Now, in the past few chapters, we have seen how energy can be released by the catabolic breakdown of carbohydrates in aerobic and anaerobic processes. However, in this chapter, we shall see how the metabolic oxidation of lipids releases large amounts or large quantities of energy through production of acetyl-CoA, NADH, and FADH2, and how lipids represent an even more efficient way of storing chemical energy. Now, section 2, catabolism of lipids. The oxidation of fatty acids is the chief source of energy in the catabolism of lipids. Triacylglycerol, main storage form of chemical energy for most organisms. Carbon chains are in a highly reduced form. Energy yield, approximately 9 kilocalorie per mole per gram of fatty acid. Oxidized is greater than that per gram of carbohydrate oxidized, approximately 4 kilocalorie per mole. Now, phosphorylglycerols are important components of biological membranes which have fatty acids as part of their covalently bonded structures. Now, in both types of compounds, the bond between the fatty acid and the rest of the molecule can be hydrolyzed. In this figure, we see release of fatty acids for future use. Here the source of fatty acids can be either a triacylglycerol here by lipases, hydrolysis by water and lipases to glycerol and free fatty acids, reuse or oxidation, or from phospholipids such as phosphatidylcholine by phospholipases and water to get glyceryl phosphorylcholine and also free fatty acids. Now, triacylglycerols and phosphoacylglycerols both have fatty acids as part of their covalently bonded structures. Bond between the fatty acid and the rest of the molecule can be hydrolyzed. Now, lipases hydrolyze lipids, while phospholipases hydrolyze phospholipids at different sites. Now, this figure shows us several phospholipases hydrolyze phosphoacylglycerols. Now, they are designated, for example, A1, A2, C, and D. So their sites of action are shown here. So, for example, phospholipase A2 cleaves here, phospholipase A1 cleaves here, phospholipase C cleaves here, and phospholipase D cleaves here. Now, phospholipase D, this one, occurs in spider venom and is responsible for the tissue damage that accompanies spider bites. Snake venoms also contain phospholipases. The concentration of phospholipases is particularly high in venoms with comparatively low concentrations of the toxins that are characteristic of some kinds of venom. The lipid products of hydrolysis, they lyse red blood cells, preventing clot formation. That's why snakebite victims bleed to death in this situation. Now, if we look at this figure, shows us liberation of fatty acids from triacylglycerols in adipose tissue is hormone dependent. Under condition of stress or fear, hormone is secreted from the adrenal epinephrine, and it binds to its receptors in the on the adipose cell, and this will activate adenylate cyclase, which converts ATP to cyclic AMP. Then cyclic AMP will activate a protein kinase, which activates a triacylglycerol lipase, which hydrolyze triacylglycerols to di and then to mono. The results are 3 fatty acids, plus 1 glycerol. Fatty acid activation. Now, fatty acid oxidation begins with the activation of the molecule called activation in lipid metabolism. Involves the formation of a thioester bond between the carboxyl group of the fatty acid and the thiol group of coenzyme A. Now, acyl-CoA synthetase catalyzes formation of the ester bond and requires ATP for its action. Esterification takes place in cytosol, but the rest of the reactions of fatty acid oxidation occur in the mitochondrial matrix. Acyl-CoA can cross the outer mitochondrial membrane, but not the inner membrane. And this figure shows us the formation of an acyl-CoA in 2 steps. Fatty acid requires ATP to form acyl adenylate intermediate. Then step 2 reacts with coenzyme A to form a thioester plus AMP, and this is called activated acyl group. And this is the overall reaction. So the activation step requires not only 1 ATP but 2 ATP. Why? Because this pyrophosphate is also hydrolyzed, so it's equivalent to 1 ATP. So always subtract 2 ATP from the total for the activation of the fatty acid. Now, acyl group is transferred to carnitine, carried across the inner mitochondrial membrane, and transferred to mitochondrial CoA by transesterification reactions. Carnitine is a molecule used in fatty acid metabolism to shuttle acyl groups across the inner mitochondrial membrane. Transesterification reactions are catalyzed by carnitine acyl transferase, which transfers a fatty acyl group to carnitine, is called carnitine palmitoyl transferase, or CPT1, which is found on the cytosol side of the inner mitochondrial membrane with a specificity for acyl groups between 14 and 18 carbons long. The acyl carnitine passes through the inner membrane via a specific translocase. Once in the matrix, the acyl group is transferred and is acted upon by carnitine palmitoyl transferase, or CPT2, which is found in the inner face of the membrane. And you look at this figure, we see role of carnitine in the transfer of acyl groups to the mitochondrial matrix. Here at the beginning we have here cytosol. Now this is the activated fatty acyl-CoA. It can cross the outer membrane and then it binds to a carnitine in the presence of CPT1, as I said, to form acyl-carnitine CoA, and then CoA go to the surface again. This now can cross by specific translocase, and now you have acyl-carnitine in the matrix side. It's also acted upon by CPT2, as I told you, in the presence of CoA, to regenerate fatty acyl-CoA and carnitine. Carnitine crosses the inner membrane back to repeat the cycle. Now here, your fatty acyl-CoA is ready for beta oxidation. Oxidation of saturated fatty acids. In the matrix, it's called beta oxidation. Repeated series of reactions that cleaves 2 carbon units from the carboxyl end of a fatty acid. It requires 4 reactions. أولا oxidation of acyl-CoA to alpha, beta unsaturated acyl-CoA catalyzed by FAD-dependent acyl-CoA dehydrogenase. Hydration of unsaturated acyl-CoA to produce a beta-hydroxy-acyl-CoA catalyzed by NOL-CoA hydratase. Third, oxidation reaction catalyzed by beta-hydroxy-acyl-CoA dehydrogenase, which is an NAD+ dependent enzyme. Fourth, cleavage of this beta-keto-acyl-CoA catalyzed by thiolase. And here, this figure shows us the beta oxidation of saturated fatty acids involves a cycle of 4 enzyme catalyzed reaction. Here, we start with this fatty acyl-CoA. Notice here, this carbon is designated alpha next to the carbonyl, and then this is called beta. Now, each cycle, now in the first step here, oxidation by acyl-CoA dehydrogenase, which is an FAD-linked dehydrogenase, to produce FADH2 and the trans delta 2 NOL-CoA. Then by a hydratase, and in the presence of water, it is converted to L-beta hydroxy acyl-CoA. and then the second oxidation by L-hydroxyacyl-CoA dehydrogenase, which is an NAD plus dependent dehydrogenase, which produces NADH, and beta-ketoacyl-CoA. And then the last step here, cleavage by thiolase in the presence of coenzyme A to generate acetyl-CoA plus fatty acyl-CoA shortened by 2 carbons. So each cycle produces one FADH2 and one NADH, and it liberates acetyl-CoA, resulting in a fatty acid that is 2 carbons shorter. Now the delta symbol here represents a double bond, and the number associated with it is the location of the double bond, based on counting the carbonyl group as carbon 1. Now this figure shows us the oxidation of stearic acid, 18 carbons, in the beta oxidation gives rise to 9 2-carbon units after 8 cycles of beta oxidation. So you see here we have 18 2-carbon units, 9, so it produces 9 acetyl-CoA, and the number of cycles of beta oxidation is 8. So the 9th 2-carbon unit remains esterified to CoA after 8 cycles of beta oxidation, have removed 8 successive 2-carbon units starting at the carboxyl end on the right. Thus, it takes only 8 rounds of beta oxidation to completely process an 18-carbon fatty acid to acetyl-CoA. Now let's look at this, the energy yield from the oxidation of fatty acids. Energy released by the oxidation of acetyl-CoA formed by beta oxidation of fatty acids can be used to produce ATP. Now 8 cycles of beta oxidation are required for the oxidation of 1 mole of stearic acid to 9 moles of acetyl-CoA, according to this equation. So the products are 9 acetyl-CoA, 8 FADH2, and 8 NADH. Now you studied in chapter 19 that acetyl-CoA goes to the citric acid cycle and produces many numbers of FADH2 and NADH, in addition to also GTP. So the 9 moles of acetyl-CoA produced from each mole of stearic acid enter the citric acid cycle again, as I said. So the products are 9 FADH2, 27 NADH, plus 9 GTP. FADH2 and NADH produced by the beta oxidation and the citric acid cycle enters the electron transport chain, and ATP is produced by oxidative phosphorylation, as we studied in chapter 20. Overall equation for oxidation of stearic acid can be obtained by adding the equations for beta oxidation, the citric acid cycle, and oxidative phosphorylation. And this table shows us a balance sheet for oxidation of 1 mole of stearic acid. Here, the activation step here consumes 2 ATP, or requires 2 ATP, and then we have here 9 acetyl-CoA. Each acetyl-CoA produces 3 NADH, 3 times 9, 27, and 9 times 1 FADH2, 9, and then reoxidation of NADH from beta oxidation cycle, minus 8 NADH molecules, and reoxidation of NADH from citric acid, minus 27. So ATP here 20, and we have here 9 GTP full, here we have 20, 67.5, and reoxidation of FADH2 from beta oxidation plus 12 ATP, reoxidation of FADH from citric acid cycle plus 13.5. So the total is 122, but we subtract the activation H step ATP requirement, so 122 minus 2, so here the net is 120. So the complete oxidation of stearic acid and 18 carbon saturated fatty acid produces 120 ATP. Now, if we look at this section 21.4, catabolism of unsaturated fatty acids and odd carbon fatty acids. Now, fatty acids with odd number of carbon atoms not frequently encountered but undergo beta oxidation. Last beta oxidation cycle of these fatty acids gives propanol-CoA. Here in this figure, we see oxidation of a fatty acid containing an odd number of carbon atoms. Here, suppose this N is 15, 15 plus 1, 16, 17. So we have 16 carbon odd numbered fatty acid. It undergoes first beta oxidation to produce how many acetyl-CoA? N 15 minus 1, 14 divided by 2 produces 7 acetyl-CoA plus 1 propanyl-CoA. Now this propanyl-CoA also come from the catabolism of some amino acids like threonine, isoleucine, and methionine. In the presence of enzyme called propanyl-CoA carboxylase, which requires ATP, it is converted to methylmalonyl-CoA. Also, this can come from breakdown of valine. Now, this undergo then rearrangement in the presence of enzyme called methylmalonyl-CoA mutase. This enzyme requires vitamin B12 or cyanocobalamin, which has a cobalt 3 ion in its active site to form succinyl-CoA, and then succinyl-CoA goes in its way in the citric acid cycle. Now, what about oxidation of monounsaturated fatty acids? Cis-trans isomerization is needed to convert monosaturated fatty acid, example methionine, oleic acid, to acetyl-CoA. Now, in the case of oleoyl-CoA, 3 beta oxidation cycle at the beginning here. We have here 3 cycles of beta oxidation. They produce 3 acetyl-CoA and leave cis delta 3 to decynyl-CoA. Then rearrangement in the presence of enol-CoA isomerase to trans delta 2 to decynyl-CoA, which then طبعا proceeds normally through the beta oxidation pathway, and it produces 6 acetyl-CoA. So, in conclusion, oxidation of unsaturated fatty acids does not generate as many ATPs when compared to saturated fatty acid with the same number of carbons. We saw for stearic acid C18-0 produces 120 ATP. However, for oleic acid C18-1 with 1 double bond produces 118.5 ATP. Now, section 5, ketone bodies formed when the amount of acetyl-CoA produced is excessive when compared to the amount of oxaloacetate available to react with it. Starvation causes an organism to break down fats for energy, leading to the production of large amount of acetyl-CoA by beta oxidation. Now, in diabetic patients, cause of imbalance is inadequate intake of carbohydrates, formed principally in liver mitochondria. Ketone bodies are the following: acetone, beta-hydroxybutyrate, and acetoacetate. Now, this acetoacetate can be used as a fuel in most tissues and organs like heart muscle and renal cortex. And this figure shows us formation of ketone bodies synthesized mainly in the liver. As we can see, the excess of oxaloacetate and acetone is known as ketosis or ketoacidosis, which the body deals with it by excreting H+ into the urine, accompanied by excretion of sodium, potassium, and water. This results in severe dehydration, which leads to diabetic coma. Under starvation conditions, the brain uses acetoacetate for energy. And this figure shows you the route for oxidation of the formation of ketone bodies synthesized in the liver. End of part 1. Thank you.